Right, so there's something I've had sitting in my notes for ages, half written, because every time I go back to it I fall down some new rabbit hole and have to start again from scratch. It's about Mount Etna. The volcano in Sicily, the proper famous one, the one that's basically always smoking gently away in photos of the Italian coast like it's got nowhere better to be. And when people think dangerous volcano, they think eruptions, don't they? Lava, fire, the dramatic bit you'd actually film. That's not really what I want to talk about tonight as it happens. What I want to talk about is something a lot slower, and honestly a bit stranger if you sit with it long enough. Etna isn't just erupting now and again the way it has done for thousands of years, which it absolutely still does, we'll get to that. It's also sliding. The whole eastern side of the mountain is very slowly creeping toward the sea, has been for decades, possibly for a great deal longer than that, and it's only in the last handful of years that anyone's worked out properly why. I genuinely don't know why that particular fact lodged itself in my head the way it did. There's something about a mountain just going, millimetre by millimetre, completely indifferent to the fact that close to 1 million people live on its slopes, and a city the size of Catania sits right at its feet, that unsettles me more than any lava flow ever has. Lava you can see coming, generally. You can watch it crawl down a hillside on the news. This you mostly can't, not without instruments buried in the seabed. Funnily enough, what got me started on this particular topic wasn't even a headline about Etna specifically. It was a much smaller article about a completely different volcano on the other side of the world, somewhere I'd genuinely never heard of that was apparently doing something similar, just creeping seaward a few centimetres a year without anyone outside a fairly small research community paying it any attention at all. That sent me off looking for other examples, and Etna kept turning up over and over as basically the best studied case anyone's got. Famous enough that there's actual data going back decades, unusual enough that researchers keep finding new things to measure, and just close enough to a major city that it's not purely an academic curiosity either. It felt like the obvious one to actually sit down and do properly, rather than skimming past in someone else's list of scary geology facts, which is honestly where I first found it. So here's the plan for the next little while. We'll go through the whole thing properly. The mythology that built up around this mountain long before anyone had the faintest idea what plate tectonics were. The actual eruptive history, because Etna has been doing its thing in front of witnesses for something like 2,700 years, which is a genuinely wild stretch of human record keeping. The slow, almost accidental detective work that figured out why one side of it is on the move. What's happened at smaller similar volcanoes nearby when a flank has actually let go. And where the science honestly stands right now, today, rather than in some imagined worst case dreamt up for a thumbnail. I'll give you the ending now, since I don't believe in making anyone wait for it. Nobody serious thinks this is happening tomorrow, or next year, or probably in any of our lifetimes. But the story of how we found out it's happening at all, and what it tells us about a mountain people have lived next to for thousands of years, is one of my favourites I've come across doing this. I think you'll enjoy sitting with it. If you're new here, hello, I do these long, fairly meandering geology and natural history videos most weeks, so stick around if that's your sort of thing. No pressure either way, mind. Get comfortable. This one's going to take a while, and that's rather the point of it. Let's start with the basics, because I think Etna gets thrown around as a name so often that people forget to actually picture it properly. It sits on the east coast of Sicily, roughly between the cities of Catania and Messina, right on the spot where the African tectonic plate is pushing up against the Eurasian one. That's not incidental, by the way, that's the whole reason it exists. It's currently somewhere around 3,400 metres tall, though I say around deliberately, because the actual figure changes after pretty much every eruption. Sometimes a crater rim collapses and it gets a bit shorter. Sometimes lava piles up and it gets a bit taller. As of a couple of years ago, it was sitting at about 3,403 metres, but by the time you're watching this, it's probably shifted again in one direction or the other. It's not a fixed number, which I quite like, if I'm honest. Most mountains don't have the decency to keep you updated. It's enormous in footprint too. The base of the thing has a circumference of around 140 kilometres, which is a properly absurd distance when you say it out loud. You could drive most of a day just going around the bottom of it. Now, the name itself. There are a couple of theories floating about, and nobody's entirely settled on one, which I find oddly comforting, because it means even the linguists are allowed to shrug occasionally. One idea is that it comes from the ancient Greek word for to burn. Another is that it traces back to a Phoenician word meaning something like furnace or chimney. Either way, you can see the theme. People have been naming this thing after fire for an extremely long time. Locally, though, it's not really called Etna at all that often. The Sicilians have their own name for it, Muncibedu, which softens in Italian to Mongibello. That one's a proper linguistic mashup, by most accounts a combination of the Romance word for mountain and the Arabic word for mountain, stitched together by people who clearly just wanted to make absolutely sure everyone understood the point. Mountain, mountain. Fair enough, really. It's not just the sheer length of the record that gets me, it's how early the detail starts. Ancient Greek poets were writing about specific eruptions by name centuries before anyone had words like volcanology. Hesiod mentioned Etna's eruptions in his own work, and there are surviving references from both Pindar and Aeschylus, describing a particular eruption generally dated to around 475 BCE, which means we've got poetic eyewitness accounts of this mountain doing its thing from roughly 2,500 years ago. That's not folklore reconstructed centuries later. That's contemporaries writing close to the event, describing something they genuinely watched happen. And the mountain's deep past goes back a great deal further than even that, obviously. Somewhere between about 35,000 and 15,000 years ago, Etna went through a notably explosive phase, producing huge pyroclastic flows and leaving ash deposits that have turned up as far away as the southern edge of Rome's modern border, the better part of 800 kilometres to the north. The structure we see today is really the product of at least two separate main eruptive centres, building on top of each other over a very long stretch of time, which is part of why the geology underneath is, frankly, a bit of a layered mess for researchers to untangle properly. What gets me about Etna, though, isn't the name or even the size, it's the paper trail. Humans have been documenting eruptions here in some written form or another for roughly 2,700 years. That's not people vaguely remember a Big Bang once. That's continuous, overlapping, generation after generation written record. There are very, very few places on Earth where you can say that. Most volcanic history has to be pieced together from ash layers and guesswork. Etna's got actual witnesses going back to antiquity, which is partly why it became a UNESCO World Heritage Site back in 2013. Not for being pretty, although it is, but for being one of the longest continuously studied volcanoes that exists. I think that's worth sitting with for a second before we go any further, because it changes the whole flavour of tonight's story. We're not reconstructing this mountain's behaviour from scraps. People have been standing at the bottom of it, taking notes, for the better part of 3,000 years, and one of the things they've been writing down, on and off, almost without realising what they were describing, is the mountain very slowly moving. But we'll get to that properly in a bit. Before the actual geology, I want to talk about what people believed was going on underneath this thing long before anyone had geology to fall back on, because honestly, some of it is more entertaining than the science. Before anyone understood plate tectonics, people still had to explain why this mountain kept grumbling, smoking, and occasionally setting fire to the landscape. And the ancient Greeks, fair play to them, came up with some genuinely committed answers. The big one involves a monster called Typhon. In the version most people tell, Typhon was this enormous, near unbeatable creature, son of the earth itself, who went up against Zeus for control of, well, everything. Zeus won, as he tends to in these stories, and rather than just locking Typhon up somewhere boring, he buried him underneath Etna. So every rumble, every burst of steam, every lava flow was supposedly just Typhon thrashing around down there, still trying to get free. I genuinely love that as an explanation. It's not subtle, but it's got a sort of poetic logic to it. The ground shakes because something furious is trapped beneath it. There's a second strand of the mythology that's a bit more industrious, less monster and more workshop. This one has the forges of Hephaestus, the god of fire and craftsmanship, tucked away underneath the mountain too, sometimes alongside the Cyclopes, hammering away at metalwork for the gods. In this version, the smoke isn't rage, it's just smoke from the world's most impressive forge. Different mood entirely. Same mountain, doing the same thing, two completely different stories about why. And then there's my favourite bit of Etna folklore, which isn't really mythology so much as one very confident man making a very bad decision. There's an old legend about the philosopher Empedocles, who reportedly became so convinced he'd transcended ordinary mortality that he climbed up to the summit and threw himself into the crater, the idea apparently being to vanish completely and let everyone assume he'd simply ascended to godhood. Tidy plan, if it had worked. According to the legend, though, the volcano spat one of his sandals back out, and that was rather the end of the mystery. I don't know how much of that story is true, and I genuinely don't think anyone does, but I love that it's survived this long purely because it's such a brilliantly petty plot twist. You try to fake your own apotheosis, and the mountain just hands your shoe back. Here's the bit that actually surprised me when I came across it though, and it's got nothing to do with the Greeks. Etna shows up in Arthurian legend. Properly, not in some loose, oh, there's a mountain in this one scene way. In medieval Breton storytelling, the name Mongabello got attached to an otherworldly underground realm, ruled over by Morgan Le Fay, and, in some tellings, by King Arthur himself, who was said to be living on inside the mountain rather than dead and buried like everyone assumed. There are even bits of medieval writing, from clergymen recording local folklore around the time of the Norman conquest of Sicily, describing this as if it were treated as more or less historical fact at the time, which is mad when you think about it. Breton storytellers, hundreds of miles from Sicily, basically picked up an old Welsh idea about a paradise hidden underground and grafted it onto this specific, very real, very smoky mountain because it already had that otherworldly reputation going for it. There's a simpler, more grounded strand of local folklore too, less mythological and more practical, the old belief that earthquakes around the mountain were simply Etna turning over in its sleep, shifting its weight the way anyone might in the middle of the night. It's a wonderfully understated way of explaining genuine seismic activity, treating it as something closer to a restless sleeper than an angry deity, and if I'm honest, given everything we'll cover tonight about gravity and slow-shifting flanks, it might be the single most scientifically accurate bit of ancient folklore in this entire section, even though nobody involved in coining it had the faintest idea why. The Arthurian material gets stranger the further you dig into it too. There are accounts from medieval clergymen, writing in Latin not long after the Norman conquest of Sicily, that don't just mention the legend in passing, they record it as something locals apparently treated as established fact, complete with a specific story about a lost horse wandering into Arthur's hidden underground kingdom beneath the mountain and eventually being returned. One of these accounts even cites a named source, a canon supposedly relaying the story second-hand, the way you'd cite a source in any other piece of reporting. It's a proper reminder that medieval folklore wasn't always treated as obviously fictional by the people recording it. As far as some of these writers were concerned, they were simply documenting a fact about the local landscape, the same way you or I might mention which motorway runs past a town. So by the time actual scientists started turning up with instruments, Etna had already done several careers as a monster's prison, a god's workshop, and a magical king's secret retirement home. Not bad going for one mountain. I think it says something about the place that none of those stories feel like a stretch once you've actually stood at the bottom of it and watched it smoke. It's the kind of landscape that makes you want to invent a myth even if you already know better. There's an interesting wrinkle to all this too, because not everyone in antiquity bought into the monster and god explanations even at the time. There's a surviving Latin poem from the early Roman period, traditionally just titled Etna, where the unknown author goes out of his way to dismiss the divine and mythological versions entirely, arguing instead for a more naturalistic explanation rooted in fire, wind, and pressure building up inside the earth itself. It's not modern science by any stretch. Plenty of it reads as guesswork dressed up in verse, but it's a genuinely striking example of someone centuries before anyone involved in tonight's later sections was even close to being born, looking at exactly the same mountain and instinctively reaching past the myths for something closer to an actual mechanism. The poetic explanations and the proto-scientific ones were apparently both circulating side by side even back then. Right, that's mythology covered. Worth knowing the actual shape of the thing now, underneath all the stories. Etna isn't really one neat cone with a single hole at the top, the way a kid might draw a volcano. It's a lot messier and more interesting than that, structurally speaking. Up at the summit there isn't just one crater, there are 4 distinct ones clustered together. The northeast crater, the Voragine, the Bocca Nuova, and a complex around the southeast crater that's grown its own little system over the years. They don't all behave the same way, or erupt on the same schedule. Sometimes one of them is the main event for years while the others just sit there steaming politely. Sometimes they all decide to have a go at once. And then, scattered down the flanks of the mountain, there are reportedly more than 300 additional vents. Some are tiny, barely more than a hole you could miss on a hike. Others have, at various points in history, opened up into proper craters hundreds of meters across. This is the bit I think people miss when they picture Etna. An eruption doesn't have to come out the top. It can open up anywhere on the sides, sometimes startlingly low down, close to where people actually live. Broadly, there are two flavours of eruption here. Summit eruptions, up at the main craters, tend to be the spectacular ones you see in the photos, fountains of lava, dramatic ash columns, but they're mostly happening high enough up that they don't threaten the towns below. Flank eruptions are the other kind, lower down, sometimes well within inhabited areas, and historically those are the ones that have actually caused damage, because the lava doesn't have far to travel before it reaches a village or a vineyard. And this isn't some rare, once-a-generation thing. Since the year 1600, there have been at least 60 recorded flank eruptions, and tellingly, close to half of those have happened since the start of the 20th century. The mountain has, if anything, been getting more active in modern record-keeping, not less, which is a slightly unsettling fact to just leave sitting there, but I promise we're building toward context, not dread. To put a finer point on that pattern, just since the year 2000 there have been 4 separate flank eruptions, in 2001, 2002 to 2003, 2004 to 2005, and 2008 to 2009, each one breaking out from a different stretch of the mountain sides rather than the summit. That's a genuinely tight clustering for a structure this size, and it's part of why volcanologists treat Etna less as a single predictable vent, and more as an entire system of possible exits, any one of which might open up next. I find that genuinely useful to know, honestly, because it reframes the whole "when will it erupt next" question. It's less about waiting for one specific crater to go off, and more about which patch of the mountain happens to give way first. What I find genuinely fascinating about all this is how it reframes Etna as less of a single event waiting to happen, and more of an ongoing process. It's not a mountain that erupted once dramatically and now sits dormant, brooding, waiting. It's a mountain that's basically always doing something somewhere on its structure, and has been for the entire span of recorded human history in the area. That constant low hum of activity is actually part of why it's become such an important place for volcanologists. You don't have to wait decades between data points. The mountain just keeps generating new ones. It's worth pausing on just how much that summit elevation has shifted over documented history, because it's a genuinely good illustration of how dynamic this thing is structurally. Back in 1865, surveyors recorded the summit as standing roughly 50 metres higher than it measured by the early 21st century, the difference mostly down to periodic collapses of the crater rim over the generations in between, each one quietly shaving height off the top, even as new eruptions kept adding material elsewhere. It's not a steady climb upward the way you might assume an actively erupting mountain would behave. It's more of a slow, lopsided wobble, gaining here, losing there, never quite settling on a final number. There are also, by most estimates, more than 200 caves scattered across the volcano's surface, almost all of them carved out by old lava flows rather than dug by anyone. Some were apparently used in antiquity as burial sites, or, slightly more practically, as natural cold storage for packing snow away through the warmer months. I rather like that detail. Long before refrigeration existed, people living on the slopes of an active volcano were using tunnels carved by its own lava to keep things cold. There's something pleasingly circular about that. All right, with that basic shape in your head, summit craters up top, hundreds of vents down the sides, fairly constant low-level activity, I want to take you somewhere a bit more dramatic. There's a valley carved into the eastern side of Etna that, when you actually look at how it got there, tells you everything about what this mountain is capable of when things go properly wrong. If you ever look at a satellite photo of Etna, there's a feature on the eastern side that looks completely out of place. It's called the Valle del Bove, the Valley of the Ox, and it's this enormous horseshoe-shaped scar gouged into the side of the mountain, roughly 7 kilometers long, 5 wide, and in places a full kilometer deep. It doesn't look like the rest of the volcano at all. The rest of Etna has that classic smooth, layered, built up over time look. The Valle del Bove looks torn. That's because it was. The current best dating, using radiocarbon analysis on debris from the valley, puts the event that carved it somewhere around 7,500 to 7,100 BCE. So we're talking roughly 8 to 9,000 years ago, which on a human history scale is genuinely ancient, but on a geological scale is practically yesterday. A huge section of the eastern flank simply gave way. Researchers have actually compared the style of failure to the famous 1980 collapse at Mount St. Helens, where the whole side of the mountain slid off in one catastrophic event rather than eroding gradually. Same basic idea, just a different continent and a few thousand years earlier. Here's the part that I think gets lost when people talk about the Valle del Bove as a pretty hiking spot, which, to be fair, it is. There's apparently a glacier in a lava cave nearby and everything. When that much material slides off the side of a coastal volcano all at once, it doesn't just disappear quietly into the landscape, it goes into the sea, and when that much rock and debris hits open water that fast, it generates a tsunami. There's been computer modelling done specifically trying to reconstruct what that ancient tsunami would have looked like, and the simulation suggests the wave would have crossed a significant stretch of the Mediterranean and reached distant shorelines within a matter of hours. Some researchers have even floated the idea that it might be connected to the sudden abandonment of a Neolithic coastal settlement over in what's now Israel, a place called Atlit Yam, which today actually sits underwater itself. I want to be honest with you that this particular connection is more speculative than confirmed. Archaeology from that far back rarely gives you a tidy smoking gun, but the timing lines up closely enough that it's a genuinely live idea among researchers rather than a fringe theory. I find this section of the story strangely calming, if that makes sense, rather than alarming. Not because a tsunami 8,000 years ago is a comforting thought exactly, but because it tells you something important about scale. This is geology operating on a timescale where recently means within the last 10,000 years. The valley isn't a warning sign that something's imminent. It's a record. It's the mountain quite literally showing its work, an old scar from one specific dramatic chapter in a much, much longer story. The physical evidence for how big that ancient collapse actually was is honestly staggering once you look at the numbers properly. Seismic surveys of the seafloor off Etna's coast have picked up a debris field connected to the Valle del Bove collapse, stretching out as far as 20 kilometers offshore, made up of somewhere between 16 and 21 cubic kilometers of material. I genuinely struggle to picture a cubic kilometer of anything, let alone 20 of them, sliding off the side of a mountain into open water in one go. One single event produced that. And interestingly, it doesn't look like it was a one-off in the geological record either. Researchers studying deposits further out in the Ionian and Sirte basins have identified a couple of earlier deposit layers, going back even further into the Pleistocene, that look like they could plausibly be evidence of previous separate sector collapses from roughly the same area of the volcano, predating the Valle del Bove event itself. So the working picture isn't one freak catastrophe and otherwise total stability. It's more, this particular flank of this particular mountain appears to have done something like this more than once, spaced out across an extraordinarily long timeline, which, again, I find more clarifying than alarming. It tells you the rough rhythm of the thing, even if it doesn't tell you exactly when the next beat falls. Researchers studying sector collapses at large volcanoes more broadly sometimes use events like this one as a loose calibration point, a real-world data point for how often, statistically, a structure of this kind might fail catastrophically over a very long timeline, even while acknowledging that one data point from one mountain doesn't make for a reliable global average. There's also a nice, almost accidental silver lining buried in all this for the people living on the mountain today. That same scarred-out valley left behind by the ancient collapse now acts as a kind of natural catch basin for a good portion of Etna's modern lava flows, channeling material away from inhabited areas down on the lower slopes rather than letting it spread unpredictably. So the scar from one ancient disaster has, in a roundabout way, ended up protecting people from smaller, more frequent ones ever since. I don't think that's any kind of cosmic justice exactly. Geology doesn't really work that way, but it's a genuinely satisfying detail all the same. And it does set a precedent worth holding on to as we go further into tonight's video. We now know, with reasonable confidence, that this particular flank of this particular mountain has failed catastrophically before. Not constantly, not regularly. Once, that we can clearly identify in 8,000 or 9,000 years of history. That's the baseline rate we're working with. Keep that number loosely in your head, not as a countdown, just as context, because it's going to matter later when we talk about what scientists actually think the odds are of anything similar happening again anytime soon. For now, though, I want to go back further than the valley itself to the slow, almost accidental way that scientists figured out the mountain wasn't just sitting there between eruptions. It was moving the entire time, right? This is the bit I actually find the most interesting in the whole story, because it's less a single discovery and more a slow accumulation of evidence that scientists kept having to reinterpret as new data came in. Properly detective work shaped, in a way I don't think people expect from geology. It starts with GPS. From the early 1980s onward, researchers monitoring Etna with land-based satellite positioning noticed something odd. The eastern flank of the mountain wasn't staying put. It was creeping, slowly, toward the Ionian Sea. Different studies measured slightly different rates depending on exactly where and when they took readings, generally somewhere in the range of a little over a centimetre a year, up to several centimetres a year nearer the coast, with one widely cited figure putting the average around 14 millimetres annually, across a stretch of the early 2000s. I'll be honest, the exact number isn't really the point, and I'm not going to keep repeating different versions of it at you all evening. The point is that it was consistently, measurably moving year after year, decade after decade, and for a long time the working assumption was that this had to be magma, rising molten rock pushing against the inside of the volcano, gradually shoving the flank outward like a balloon being inflated unevenly. Made sense, on paper. Except it didn't quite explain everything. The real shift happened when a team led by a researcher named Morelia Urlaub at GEOMAR, a German ocean research institute, decided to try something nobody had really done properly at a volcano before. Instead of just measuring the part of Etna sticking up out of the water, they went underneath it. In 2016, they placed a network of acoustic transponders directly on the seafloor, spread out across the fault line where the moving part of the flank meets the presumably stable part. These things essentially ping each other every hour and a half using sound, and because the speed of sound through water is well understood, you can work out the distance between them to within a fraction of a centimetre. It's a wonderfully patient kind of science. You just leave it running and wait. And what it picked up was genuinely surprising. The seafloor sensors showed movement happening in parts of the flank that were a long way from the volcano's actual magma source, areas where, if the old theory were correct, you really shouldn't expect to see much shifting at all. That mismatch was the clue that broke the case open, so to speak. If rising magma were the main driver, the movement should be concentrated close to where the magma actually is. It wasn't. The whole flank, including bits with no obvious connection to the plumbing of the volcano, was on the move together. Then, in May of 2017, the network caught something even more striking. A slip of over 4 centimetres across roughly an 8-day stretch, with no eruption happening at the same time at all. No fountain of lava, no dramatic news footage, nothing visible from the surface whatsoever. Just the seafloor, quietly, deciding to move a few extra centimetres while everybody above water carried on with their day completely unaware. Put together, that evidence pointed toward a different explanation entirely, and it's the one that's generally accepted now. It's not primarily magma pushing the flank outward, it's gravity. Etna is, when you get down to it, just an extraordinarily heavy thing sitting on ground that isn't all that good at holding it in place, and its own weight is doing most of the work of sliding it seaward, slowly with the occasional faster slip thrown in. We'll get into exactly why the ground underneath it behaves that way in a moment, because honestly it's a satisfying answer once you hear it. It's worth knowing that this wasn't a quick in-and-out research trip either. The network stayed in place, recording continuously, from April 2016 through to July 2017, the better part of 15 months of essentially uneventful pinging before the May 2017 slip event actually gave them something dramatic to report. That's the bit of science I think people underestimate the most, the sheer patience involved. Nobody knew in advance when, or even if, something worth writing up would happen during that particular window. The team set the equipment, went home, and waited, fully prepared for the possibility that they might come back a year later with nothing more exciting than a long, flat, boring line on a graph. The project itself had a name, rather a charming one if you're into that sort of thing, MAGOMET, short for Marine Geodesy for Offshore Monitoring of Mount Etna, and it was a proper international effort, bringing together the GEOMAR Institute in Germany, Kiel University, and Italy's own INGV, the same body that runs the day-to-day volcano monitoring we'll talk about a bit later. What they ended up with, by most accounts, was the first time anywhere in the world that this kind of slow underwater slip event at a volcano's flank had been directly measured using seafloor instruments rather than inferred indirectly from onshore data. Not just a new finding about Etna specifically, in other words, but genuinely a new technique proven to work for the very first time on this mountain, which other research groups studying other coastal volcanoes elsewhere have since been able to draw on. The same network, as it happens, kept right on working through some properly turbulent periods afterward too, including capturing data straight through Etna's unusually active spell in February 2021, when the volcano produced an extraordinary run of paroxysmal episodes in fairly quick succession. Having a continuous instrumental record spanning both quiet years and genuinely eventful ones is enormously valuable for researchers, because it lets them start comparing flank behaviour during calm periods against flank behaviour during active eruptive periods directly, rather than relying on guesswork about whether the two might be connected. It's the kind of long, unglamorous data set that doesn't make headlines on its own, but that ends up being exactly what eventually allows a clearer, more confident answer to emerge further down the line. But I wanted to spend proper time on this discovery itself first, because I think it's a lovely example of how science actually works most of the time. Not some dramatic eureka moment, but years of patient measurement, an assumption that seemed reasonable for a long while, and then a stubborn little inconsistency in the data that eventually forced everyone to rethink the whole picture. If it's gravity rather than magma doing most of the work, what does that actually mean in practice? I had to sit with this one for a bit before it clicked properly, so let me try and walk through it the way it eventually made sense to me. Picture Etna not as a solid block sitting on solid rock, but as an enormous weight sitting on top of a layer of much softer, weaker material underneath, specifically old sedimentary clay that happens to slope gently away toward the sea. The volcano itself is mostly built from layer upon layer of hardened lava, which is heavy stuff, and it's been piling up on top of that softer clay base for hundreds of thousands of years. Under that kind of weight, over that kind of timescale, on ground that's already tilted toward open water, things shift. Not dramatically, not all at once, just a slow, continuous creep in the direction gravity and the slope are already pointing it. A bit like a very, very slow landslide that's been going on so long it barely registers as one. This is sometimes called gravitational spreading, and it's actually a recognised pattern at large volcanoes generally, not some one-off Etna quirk, which we'll come back to in a bit when we look at a few other mountains doing something similar. But Etna's specific case is a particularly clean example of it, partly because of that clay layer underneath acting almost like a lubricant, and partly because the GOC underwater data gave researchers a way to actually watch it happening offshore in real time, rather than just inferring it from older land-based measurements. Now, here's the bit where I have to be honest with you rather than just reassuring, because I think you deserve the straight version rather than a softened one. The 2018 study that came out of all this seafloor work didn't just say, the flank moves, interesting, end of story. It concluded that the researchers couldn't entirely rule out this movement eventually evolving into something more sudden, a more catastrophic failure of the flank, which is the scenario that would actually generate a serious tsunami rather than just being a curious slow-motion geology fact. That sounds properly worrying written down like that, I know. But, and this matters a great deal, the same body of research carried the caveat attached to almost every serious statement made about it since. The lead researcher on that very study told reporters at the time that the immediate risk is considered low. And in a separate interview, when pressed on what eventually might actually mean in practical terms, the honest answer given was that it might not happen for another 100,000 years. Possibly longer. Nobody's actually claiming to know. I think that's the bit worth sitting with properly rather than rushing past. Scientists confirmed something genuinely significant here. That a major coastal volcano is sliding due to its own weight, rather than internal pressure, and that the long-term possibility of catastrophic failure can't be mathematically excluded. That's a real finding, and it deserves to be taken seriously as exactly that. But can't be excluded and expected are two very different sentences, and the people who actually did the research have been fairly consistent about not blurring the two together. It's the kind of nuance that gets lost the moment a headline writer gets hold of it, understandably because scientists can't rule something out over an unspecified, possibly enormous time frame, doesn't exactly leap off a thumbnail. But it's the actual honest shape of where the science currently sits. It's also worth saying that gravity being the main driver doesn't mean magma plays no role at all. The picture's a bit more tangled than a clean either-or. There's a well-documented event from December 2018, when a sudden intrusion of magma beneath the volcano triggered a short eruption alongside a burst of intense seismic activity, including a shallow earthquake right at the edge of that sliding eastern flank. Researchers studying the event afterward concluded the magma intrusion itself had added enough extra stress to the surrounding rock to help trigger that earthquake, suggesting the two processes, gravity's slow background creep and the occasional shove from rising magma, aren't entirely separate stories happening side by side. They interact, at least sometimes, with magmatic activity apparently capable of giving the already sliding flank an extra little nudge during specific episodes. I think that's a useful complication to sit with rather than something to worry about specifically. It doesn't change the headline finding, gravity's still doing the bulk of the long-term work, but it's a good reminder that real geological systems rarely sort themselves into perfectly tidy single-cause explanations. Mount Etna's flank is being shaped by an enormous heavy structure slowly succumbing to its own weight on weak ground, with the volcano's own ongoing eruptive activity occasionally adding extra stress into that same system at the edges. Two processes, mostly independent, sometimes overlapping, both genuinely part of the full picture. If you want a slightly daft mental image to hang all of this on, I think of it a bit like an enormous trifle left sitting on a table that isn't quite level. Nothing dramatic happens in any given minute, there's no sudden collapse, but very, very slowly, the whole thing inches toward the low side simply because that's the direction. Gravity and the slope of the table are both pointing it. Give that process 8,000 years, and every so often the structure overbalances enough that a proper chunk slides off in one go. It's not the most dignified comparison for one of the most studied volcanoes on Earth, I'll grant you. But it's the one that finally made the physics click for me, so I'm keeping it. That's the theory side of it covered anyway. It's worth grounding all of this in something a bit more concrete now, because this exact mechanism, a volcanic flank giving way and generating a wave, has actually happened in recent memory, not 8,000 years ago, just down the coast. I mentioned a moment ago that this isn't purely a theoretical mechanism. There's a real, modern, documented example, and it happened not all that far from Etna at all, on a much smaller volcanic island called Stromboli. Stromboli is one of the Aeolian Islands off the north coast of Sicily, and it's famous in volcanology circles for basically never properly stopping. It does these small, fairly rhythmic explosions more or less constantly, which is its own fascinating thing, but on the 30th of December 2002, something different happened. There's a slope on the island called the Sciara del Fuoco, which translates roughly to stream of fire, a steep scarred flank that's actually the result of previous collapses going back thousands of years, not unlike the Valle del Bove in that sense. On that particular afternoon, the seismic network picked up two large landslides along that slope, the first one starting at around 1:15 in the afternoon, the second following roughly 7 or 8 minutes later. Both involved a mix of material above and below the waterline giving way more or less at once, and because it happened so close to the coast, the resulting tsunami had almost no travel time at all. Waves reaching up to 10 meters hit the inhabited side of the island in under 4 minutes from the first landslide. 4 minutes. That's barely enough time to register what's happening, let alone organize an evacuation. Remarkably, nobody died. There was real damage to buildings along the coast, and the island did go through proper emergency evacuation procedures in the aftermath, but the casualty count stayed at 0, which by most measures of these events is something close to a minor miracle of timing and geography, rather than a guarantee of how it would always go. Sailors have apparently been using Stromboli's constant glow as a navigational reference for so long, it picked up the nickname Lighthouse of the Mediterranean, which I think is a rather brilliant bit of branding for a volcano. Genuinely useful and mildly terrifying in roughly equal measure. It's been doing this, more or less without a proper extended break, for somewhere in the region of the last 2,000 years. That kind of relentless, near-constant activity is part of why Stromboli ended up being such an important place for volcanologists generally, not just for the 2002 event we've been discussing. An entire style of eruption, mild, rhythmic, explosive, gets named directly after it, Strombolian activity, a term volcanologists now use as standard shorthand for similar behaviour at other volcanoes worldwide, Etna included on occasion. I bring this up not to scare you genuinely, but because I think it's useful as a sort of scaled-down, real-world demonstration of the actual mechanism we've been talking about all evening. This wasn't some ancient half-mythologized event reconstructed from sediment cores. This happened within the lifetime of most people watching this. A volcanic flank gave way, a chunk of it slid into the sea, and a real tsunami followed within minutes at an Italian volcano in this century. The physics isn't speculative. It's been observed directly, with seismographs running and people on the ground describing exactly what they saw and felt. It's also not as though 2002 was some completely unprecedented one-off for that particular slope either. Researchers have documented 6 separate tsunamis generated by landslides along the Sciara del Fuoco, going back to the early 20th century, which makes it one of the more reliably tsunami-prone single slopes anywhere in Italy. The 2002 event just happens to be the best studied, partly because it's recent enough that there were proper instruments running and people available to interview afterward. Some of those eyewitness accounts are genuinely striking, the kind of detail that doesn't usually survive in older historical records. People close to the slope reported watching the sea visibly pull back from the shoreline right before the wave hit. A classic and frankly quite eerie warning sign that anyone who's read much about tsunamis elsewhere in the world will probably recognise. Surveys done afterward using sonar mapping found the underwater landslide had left a scar roughly 650 metres wide carved into the seafloor. A genuinely substantial chunk of the slope simply gone, relocated into deeper water in the space of a few minutes. What's different about Etna, and worth being clear about, is scale and mechanism. Stromboli's collapses were tied closely to active eruption, and a relatively small, steep, already unstable slope built up from loose volcanic material. What's happening at Etna is a far larger, far slower, gravity-driven creep across an enormous flank. With no clear sign it's accelerating toward anything resembling a Stromboli-style event anytime soon. They're related phenomena, cousins rather than twins. But Stromboli does answer one fairly natural question people tend to have when they first hear about Etna's slide. Could something like this genuinely happen at a real, modern, populated Italian volcano? The answer demonstrably is yes, it already has, just at a different one, on a different scale. Let's widen the lens a bit further now, because Etna and Stromboli aren't actually unique in dealing with this kind of slow instability. It turns out to be a recognisable pattern at coastal and island volcanoes right around the world. I think it's easy, when you're deep in researching one specific volcano, to start treating it like it's uniquely cursed somehow. So I want to take a short detour and put Etna in some company, because honestly, it makes the whole picture feel less ominous, not more. A genuinely useful comparison sits over in Indonesia, at a volcano called Anak Krakatau, which translates to Child of Krakatoa, because it literally grew up out of the underwater caldera left behind by the much more famous 1883 eruption. In December 2018, part of that island's flank collapsed into the Sunda Strait, and because the failure happened without any large preceding earthquake, the kind that normally triggers a tsunami warning, there was essentially no advance notice for coastal communities. The resulting tsunami struck without the usual warning signs people are trained to look for, and it was genuinely devastating, killing several hundred people along the coasts of Java and Sumatra. I'm not going to dwell on the numbers, it's a properly tragic event and not the focus of tonight, but structurally it's almost a textbook version of the exact mechanism scientists are watching for at Etna. Gravity-driven flank failure, an island volcano, water close by, sudden displacement. Different ocean, same underlying physics. Then there's the more famous, and honestly more complicated case of La Palma in the Canary Islands, specifically a ridge called Cumbre Vieja. Back in the early 2000s, a couple of researchers put forward a hypothesis that a future eruption there could trigger a colossal flank collapse, and that the resulting wave could, in the most extreme version of the scenario, cross the entire Atlantic and cause damage on the east coast of the United States. It made for genuinely gripping documentary television at the time, and to be fair to the original researchers, the underlying mechanism they were describing, gravitational flank instability, is real and well established. It's the same family of process we've been discussing all evening. But over the following years, a great deal of follow-up work from other volcanologists pushed back fairly hard on the specific scale of that doomsday scenario. Arguing the volumes involved and the way a collapse would most likely actually unfold made a transoceanic mega-tsunami a far less likely outcome than the original headline suggested. I think that's a genuinely useful story to know going into the rest of tonight's video, not because it means we should dismiss every alarming volcanic headline out of hand, but because it's a good reminder that the gap between a real, published, physically plausible mechanism and the most dramatic possible version of that mechanism reaching every audience can be enormous. Both things were true at once. The hazard was real. The worst-case framing got ahead of the science. And it's not just volcanic islands surrounded by ocean either. Volcanoes built on land but near coastlines, including some in Hawaii, show their own versions of this same slow, gravity-driven seaward creep, simply because of how heavy these structures get and how they're sitting on ground that isn't always perfectly suited to holding all that weight still. It's a recognized category of geological behavior, studied at multiple sites by multiple independent research groups, not some one-off oddity that happens to be plaguing poor unlucky Etna specifically. Hawaii is a particularly good comparison case, as it happens, because researchers have actually been studying flank movement there for even longer than they have at Etna. The southern flank of Kilauea, one of the most active volcanoes on the planet, has been measured creeping seaward for decades, driven by broadly the same combination of sheer structural weight and a weaker layer underneath providing relatively little resistance. Offshore from the Hawaiian Islands generally, surveys of the seafloor have mapped out absolutely enormous ancient landslide deposits, evidence of past sector collapses on a scale that, frankly, makes Etna's Valle del Bove event look comparatively modest. What that tells researchers, broadly, is that big basaltic volcanoes built up close to open water seem to more or less inevitably end up dealing with this kind of structural instability eventually, given enough time. It's less a quirk of any one location, and more a fairly predictable consequence of physics, heavy material, weak foundations, gravity, water nearby, repeated across multiple volcanic settings on opposite sides of the planet. UNESCO has even run dedicated missions specifically to assess this category of risk closer to home for Etna too, sending researchers out to the nearby Aeolian Islands a few years back to investigate underwater volcanic hazards in that immediate region more broadly, Etna and Stromboli both included in that wider umbrella of attention. There's a whole loosely connected international research community built around exactly this question now, comparing modelling techniques and monitoring approaches across volcanic sites in the Pacific, the Atlantic, and here in the Mediterranean, swapping notes on what's worked and what hasn't at each location. Findings from the Hawaiian studies have fed back into how researchers think about Etna's data, and the Etna seafloor methods have in turn started getting tested at other volcanoes elsewhere that previously had no underwater monitoring of their own at all. It's a genuinely collaborative, slowly accumulating body of knowledge, rather than each research group quietly reinventing the wheel in isolation every time a new mountain catches their attention. I find that sort of quiet, unglamorous international cooperation rather heartening, if I'm honest, tucked away behind all the more dramatic headlines this kind of research occasionally generates. I find that reassuring, oddly. Not because any individual case stops mattering once you know it's part of a pattern, but because it means there's a whole community of scientists working across continents, comparing notes, refining models, learning from each new bit of monitoring data at every single one of these sites. Etna isn't being watched in isolation by one slightly anxious research group. It's part of a much bigger, much older conversation about how heavy volcanic mountains and gravity and slow geological time all interact, and that conversation has been going on, in one form or another, for decades. Speaking of being watched, that actually brings me nicely to what I think might be my favourite part of this whole story. How scientists are actually keeping tabs on Etna today, right now, with some genuinely clever bits of kit. Etna might genuinely be one of the most closely watched volcanoes on the planet, and I don't say that lightly because there's a properly enormous amount of equipment trained on it at all times. On land, there's a dense network of more than 50 seismometers scattered across the mountain, which is honestly more than I expected for one single peak, picking up the constant low hum of tremor and the sharper signals of actual earthquakes, most of which are far too small for anyone to feel, but tell volcanologists an enormous amount about what's happening underground. Alongside that, there are GPS stations tracking ground deformation, essentially watching for the mountains swelling or shifting in ways that might hint at magma moving closer to the surface. There are visible and infrared cameras running around the clock at the summit craters, gas sensors tracking changes in sulfur dioxide and carbon dioxide output, and satellite data layered on top of all of it, watching for thermal anomalies from space. All of that feeds back continuously to a monitoring centre run by Italy's National Geophysics Institute, INGV, based in Catania, where volcanologists are assessing the data more or less constantly. That's the land-based side, and it's been built up over decades. But the part of this story I find genuinely delightful is the underwater side, because that's a much newer, much trickier problem, and the people working on it have had to get properly inventive. We touched on the acoustic transponder network already, the one that first caught that telltale underwater movement back in 2016 and 2017. That network's still running, and it's actually being expanded. In early 2024, a research expedition went back out to add a new kind of instrument to the setup, devices called piezometers, which measure pressure and temperature within the top few meters of seafloor sediment. The thinking is that as a section of the flank shifts, it should produce small, detectable changes in pore pressure and temperature in the ground around it, changes that might, with enough data over enough time, end up being an early indicator of movement before it actually happens, rather than just a record of movement after the fact. They're essentially trying to give the mountain's underwater foot a sort of nervous system, a way to feel it twitch before it actually takes a proper step. There's also a separate but related project keeping an eye on something called the North Alfeo Fault, a seismic feature near the base of Etna offshore in a heavily populated stretch of coastline. That project's specifically trying to understand the seismic processes happening along that fault, partly because earthquakes and flank movement in this kind of setting aren't always entirely separate phenomena. They can feed into and influence one another in ways researchers are still working out. It's worth dwelling for a second on why the underwater monitoring took so much longer to get going than the land-based side, because the reason is almost embarrassingly simple once you hear it. Satellites are brilliant at watching ground deformation from space, but the radar and GPS signals they rely on simply don't travel through water in any useful way. The moment you go below the surface, all of that decades of satellite expertise becomes essentially useless, and you're forced back onto much older, slower, more hands-on methods. Sound waves bounce between physical instruments sitting on the seabed. It's a proper reminder that even with all our modern satellite infrastructure, there are still entire categories of the planet that have to be measured the genuinely old-fashioned way, one careful deployment at a time. There's also a properly honest bit of research history worth mentioning here, because I think it's a nice corrective to the idea that scientific monitoring always goes smoothly. A separate land-based sensor network was deployed across Etna starting in 2019, designed to track things like ground vibration and environmental conditions continuously using fairly modern, low-power wireless sensor technology. During a particularly intense period of eruptive activity in 2021, which produced more than 60 individual paroxysmal episodes that year alone, most of the sensors left near the summit were simply destroyed outright, by ash, by storms, by the sheer hostility of being parked on an active volcano during one of its busier years. The team had to go back, relocate the more vulnerable equipment further away from the summit into more sheltered spots, and effectively rebuild parts of the network before getting it properly running again a couple of years later. I like including that bit because it's honest about the field. Monitoring an active volcano isn't a tidy, set it and forget it process. Equipment gets wrecked, plans change, people go back out and try again anyway. Most of this monitoring data, reassuringly, isn't locked away in some inaccessible academic archive either. ENGV publishes regular bulletins covering seismic activity, ground deformation, and volcanic gas readings, openly available for anyone who wants to actually look, alongside near-constant webcam feeds trained on the summit craters that genuinely anyone with an internet connection can check at more or less any hour of the day or night. I think that transparency matters more than it might initially seem. It means the people living closest to the mountain aren't relying purely on official reassurance from a distance. They can, if they're so inclined, go and look at more or less the same raw data the volcanologists themselves are working from. What strikes me most about all of this, honestly, is the tone of it. Nobody installing piezometers off the Sicilian coast in 2024 is doing so because they think collapse is imminent. They're doing it because this is a fundamentally interesting, still partly mysterious bit of Earth science, and Etna happens to be an unusually good natural laboratory for studying it properly. It's curiosity-driven work carried out by patient people who are happy to wait years for a meaningful data point. That's a very different energy from crisis response, and I think it's worth keeping that distinction in your head as we go further into tonight's video. It's probably time to come back to the human side of all this for a bit too, because for as much as we've been talking about clay layers and acoustic transponders, there are an awful lot of people who've actually had to live alongside this mountain, sometimes through genuinely dramatic moments in its history. If you want one story that sums up the relationship between Etna and the people living next to it, I think it's the eruption of 1669, which is generally reckoned to be the most significant eruption in the volcano's recorded history. It started in March that year, with weeks of unsettling earthquakes building up beforehand, the kind of warning signs that, with hindsight, were obviously building towards something. When the eruption itself began, lava started working its way down the southern flank, and over the following weeks it swallowed a string of villages, places like Nicolosi and Mascalucia, before heading, with what must have felt like grim inevitability at the time, toward the city of Catania itself. Catania had old defensive walls, and remarkably, those walls actually held the lava back for around 15 days, which is a genuinely impressive feat of accidental engineering considering they were built to stop people, not molten rock. Eventually, though, in late April, parts of the flow did overtop the walls and push into parts of the city, though by most accounts it caused comparatively limited destruction once inside, nudging aside weaker structures rather than levelling the place outright. The bulk of the flow carried on past the city and into the harbour, where it actually extended the coastline outward by something like 800 metres. There's a lovely, slightly surreal detail attached to this. The medieval Castello Osino, which had originally been built right on the seafront specifically for coastal defence, ended up stranded a fair distance inland once the new lava-built land had finished cooling around it. It's still there today, this old seaside fortress, now sitting nowhere particularly near the sea, purely because of what happened in 1669. There's also a small, very human detail from partway through the eruption that I'm fond of. A local priest named Diego Pappalardo apparently organised a group of 50 or so men to try and divert the flow by physically breaking open the hardened crust on one side of the channel, redirecting molten lava away from Catania. It actually worked for a while, except the new direction it took threatened a different town entirely, whose residents, understandably furious, chased Pappalardo and his crew off before the lava could be redirected back toward the original path. I think about that a lot, honestly. Even in the middle of a genuine natural disaster, there's still room for one town's solution becoming another town's emergency. I do want to be honest with you about something here because I think it matters for how we talk about disasters generally, not just this one. You'll often see this eruption described with absolutely enormous casualty figures attached to it, sometimes numbers in the tens of thousands. But when you actually go back and look at the contemporary written accounts, from the time, in both Italian and English, the surviving records are oddly precise about the number of buildings destroyed and the area of farmland lost, and yet they don't actually report deaths directly attributable to the lava itself. The bigger casualty figures appear to have been added or inflated somewhere along the way in later retellings, the way these things sometimes do. I find that genuinely interesting in its own right, less about the number itself and more about how stories about disasters can pick up extra weight the further they travel from the original sources. It's a useful little reminder to hold on to for the rest of tonight, honestly. The eruption actually carried on for months after the lava reached Catania, not winding down properly until around July of that year, by which point it had reshaped the local landscape in ways that are still visible today if you know where to look. There was an old lake on the southern slope, in existence since Roman times apparently, that simply vanished under the new lava entirely, and a river that used to run right through the middle of Catania, the Aminano, disappeared from the surface for some time afterward too, forced underground by the new layers of rock piling up above its old course. It didn't stay gone, mind you. The water found its own new route beneath the city and eventually re-emerged near the coast, where it still surfaces today as the Amenano Fountain, a genuinely pretty spot in Piazza Duomo right in the historic centre, that most visitors to Catania have absolutely no idea is fed by a river that got rerouted by lava over 350 years ago. I love that kind of detail, honestly. A perfectly ordinary photogenic little fountain in a city square, with a backstory involving molten rock burying an entire waterway and forcing it to find a new way to the sea over the following decades. It's a small thing, in the scheme of an eruption that destroyed a dozen settlements and reshaped a coastline, but it stuck with me more than almost any other single detail from this whole story. Most of the dramatic stuff a city goes through during a disaster gets cleaned up, rebuilt over, eventually forgotten by anyone who wasn't there. A river quietly finding its own way home underground and popping back up centuries later, in a fountain people walk past every single day without a second thought, feels like a rather gentle kind of permanence by comparison. It's also not the only time lava from Etna has physically extended Sicily's coastline outward either, just the most famous instance of it. Several flows over the centuries have reached the sea and cooled into new land, which means a measurable stretch of Sicily's eastern shoreline today is, quite literally, relatively recent volcanic rock rather than older bedrock. There's something I find genuinely striking about that, a country's actual landmass slowly growing, in fits and starts, because of the same process that occasionally threatens the towns built on top of it. The same mountain that destroys things periodically is also, almost as a side effect, the reason there's more solid ground to live on in the first place. There's a fresco in Catania's cathedral, painted not long after the eruption by a local artist called Giacinto Platania, who'd actually grown up right on that stretch of coast where the lava met the sea. By most accounts it's remarkably accurate, getting the topography and the path of the flow more or less spot on, down to the way it diverted around the city walls and through the moat of that stranded castle. I rather like that the most lasting artistic record of this whole event was made by someone who genuinely watched it happen from close range, rather than someone romanticising it from a comfortable distance afterward. Given everything we've just gone through, you'd be forgiven for assuming people might want to keep their distance from this mountain. They very much don't. Something in the region of 1 million people live on Etna's slopes today, and honestly, once you understand why, it makes complete sense. Volcanic soil is extraordinarily fertile, full of minerals that ordinary soil just doesn't have in the same concentration, and the lower slopes of Etna take full advantage of that. There's a proper wine region up there now, Etna Dock, producing bottles that get taken seriously by people who know far more about wine than I do. There are pistachio groves around the town of Bronte that are apparently rather famous in culinary circles. Citrus orchards, olive groves, all thriving on ground that, geologically speaking, is essentially cooled lava with extra steps. There's also a slightly bizarre tourism angle to all this that I genuinely enjoy. You can ski on Etna. There are actual ski resorts on the slopes of an active volcano, which feels like it shouldn't be allowed, but absolutely is. There's a cable car, the Funivia dell'Etna, that takes visitors most of the way up toward the summit craters, and a whole regional park with lava caves you can walk through, including one called the Grotta del Gelo, the ice cave, where, almost contradictorily, a small permanent glacier has formed inside a volcanic cavity. An ice cave inside a volcano. I don't entirely understand how I feel about that, but I do find it delightful. What I think is genuinely lovely, though, is the relationship locals seem to have with the mountain, at least going by how it's talked about and written about. That old nickname, Mongibedu, isn't used in some wary, nervous way. It comes across more affectionate than anything, the sort of name you'd give something enormous and occasionally difficult that's nonetheless just always been part of the furniture of your life. Generations of people have built towns on the cooled lava of previous eruptions, named their wine after the mountain, and arranged their entire calendar of skiing and hiking and harvest seasons around its moods, without that meaning they're naive about what it's capable of. I think it's less ignoring the risk and more a particular hard-won kind of comfort that comes from genuinely knowing a place, warts and all, rather than just being frightened of it from a distance. A fair chunk of the upper mountain is formally protected too inside the Parco dell'Etna, a regional nature park established back in 1987 specifically to make sure this landscape stays properly looked after as both a tourist destination and a genuine working research site. Within it there's an area called the Crateri Silvestri that gets compared, fairly often and fairly accurately by most accounts, to walking across the surface of the moon, an expanse of dark, barren volcanic ground with almost nothing growing on it, sitting in stark contrast to the lush citrus groves and vineyards just a bit further down the same mountain. It's a proper reminder of just how much variety exists across Etna's different altitude zones. You can go from genuinely otherworldly, ash-grey moonscape near the summit, down through forested middle slopes, and end up at fertile lower ground, producing some of Sicily's most highly regarded wine and produce, all within the same single mountain, sometimes within a single day's walk. And on the food side specifically, I think it's worth dwelling on for a second just how directly the volcano shapes what actually ends up on the table down there. The specific mineral content in volcanic soil genuinely changes how grapes and olives and citrus develop, which is part of why Etna Dock wines and the local olive oil have built up such a particular sought-after reputation among people who take that sort of thing seriously. It's not just marketing language stuck on a label because volcano sounds dramatic and sells well. The actual chemistry of the ground really is doing something different here compared to ordinary farmland, and generations of local growers have built entire livelihoods around understanding precisely how to work with that, rather than around it. I think there's something worth taking from that, honestly, as we head into the back half of tonight's video. We've spent a fair amount of time on slow-motion catastrophe and ancient collapses and tsunami physics, and rightly so, it's a fascinating bit of science. But the actual day-to-day reality on Etna for the people who live there is mostly about wine harvests and ski seasons and a mountain that occasionally puts on a spectacular but largely manageable light show. Worth keeping both of those things true in your head at once. Worth bearing all that in mind for what's coming next too, because the mountain itself has hardly been sitting still while we've been talking about wine and ski lifts. It's actually been rather busy lately. I think it's worth pausing the history and the deep time stuff for a moment, and just looking at where Etna actually is, activity-wise, as of right now, because it's genuinely been a busy stretch. Going back through the last year or so, Etna's had several distinct eruptive phases, each with its own slightly different character, which is apparently quite interesting from a volcanological point of view, different vents behaving differently within a fairly short window of time. One phase around the middle of last year sent an ash plume up to something like 21,000 feet, enough to disrupt local air traffic for a stretch. Then, on Christmas Eve, the northeast crater, one of the 4 main summit craters we talked about earlier, woke back up after very nearly 30 years of sitting quietly. 30 years! That's a proper long nap by any mountain standards. It came back with lava fountains and ash emissions, and the activity carried on shifting between the different summit craters into the new year, with the Vorogin crater taking over as the main event for a stretch, sending lava flows down into the Valle del Bove, that same ancient collapse scar we spent a whole section on earlier. And most recently, just in the last few days as I'm putting this together, a new vent opened up near the northeast crater, sending a slow lava flow out toward a nearby valley. By most descriptions, it's a fairly sluggish, high viscosity flow, the kind that creeps rather than races, and it's not been flagged as any threat to residential areas. It's worth understanding briefly how these updates actually get communicated in practice, because I think it demystifies the whole thing nicely. INGV uses a 4-color aviation alert system to flag changes in activity level to airlines and air traffic authorities, running from green, meaning background activity only, up through yellow and orange to red, the highest level, reserved for genuinely significant eruptions producing substantial ash. Most of what's happened over the past year or so has bounced between yellow and orange, occasionally brushing red during the more intense ash-producing episodes, which gives you a sense of where on the spectrum this recent activity has actually sat. Properly active, genuinely worth tracking if you're a pilot or an airport, but a long way short of the kind of event that would suggest anything structurally unusual happening beneath the surface. One of last year's more interesting episodes, going back to around the middle of 2025, involved the Vorogin crater waking up after more than 3 years of relative quiet, starting small with spattering lava at a newly opened vent before gradually building into something more vigorous, jets of incandescent material rising several tens of meters above the crater rim, with a new small scoria cone slowly growing inside the crater itself over the following days. That kind of gradual build, from a quiet trickle to something properly dramatic over the course of a week or two, is apparently a fairly typical pattern for Etna specifically, rather than the more sudden, all-at-once style you sometimes see at other volcanoes elsewhere in the world. It tends to give people, and instruments, a reasonable amount of warning that something's building, rather than catching everyone out with no notice at all. I find that gradual build pattern genuinely reassuring as a piece of context, separate from everything we've discussed about the flank itself. It means the day-to-day eruptive activity people associate most strongly with Etna, the bit that actually makes headlines and disrupts flights, is, on the whole, a fairly well-behaved, fairly well-telegraphed process by volcanic standards. The mountain tends to clear its throat audibly before it really gets going. Here's the bit I genuinely love, though. One of the volcanologists who actually monitors Etna day to day, a man called Boris Benka, who works for INGV and has clearly seen rather a lot of these events over the years, gave a wonderfully understated reaction to this latest bit of activity. He basically said it felt a bit too much like déjà vu, and that in his own words, it was premature to be talking about any kind of alarm. I love that response, honestly. Here's someone whose entire professional life revolves around watching this mountain extraordinarily closely, and his gut reaction to a brand new eruption was something closer to mild déjà vu than concern. I think that tells you almost everything you need to know about how to hold this whole topic in your head. Etna erupting, even fairly dramatically, is Tuesday-level normal for the people who study it. It's not synonymous with the flank suddenly deciding to go. Those are two genuinely different processes happening on two genuinely different timescales, one measured in days and weeks, the other in centuries or millennia. And conflating the two is, I think, where a lot of the more breathless headlines about this mountain tend to go wrong. So if you came into tonight half expecting some dramatic, "the volcano is about to collapse" update, I'm sorry to disappoint you, but also, honestly, good. The current activity is the mountain doing what it's done thousands of documented times before. Nothing about it suggests the slow seaward creep we spent earlier sections on is suddenly speeding up toward anything. There's a much bigger, much quieter conversation worth having now too, about the whole Mediterranean, not just this one mountain, and I think it deserves its own bit of context. Here's something I genuinely didn't know before I started digging into all this, and I suspect a fair few of you watching won't either. Most people picture tsunamis as a Pacific Ocean problem, fair enough given how much footage exists of major Pacific events. But the Mediterranean actually has the second highest number of historically recorded tsunamis of any sea basin on the planet, beaten only by the Pacific itself. It's just that they tend to be smaller, more locally contained, and a lot less documented on camera, simply because of when most of them happened. UNESCO's Intergovernmental Oceanographic Commission has actually put out a fairly stark statistical statement about this. Their assessment is that there's effectively 100% chance of a tsunami at least a metre high occurring somewhere in the Mediterranean within the next 30 to 50 years. Now, I want to be really careful with how I frame that number, because it's easy to hear 100% chance attached to Mediterranean tsunami and immediately picture Etna's flank giving way specifically. That's not what this statement is actually about. It's a basin-wide statistical projection covering the whole range of possible triggers across the entire region: earthquakes along various fault lines, smaller localized landslides, underwater volcanic activity at several different sites, not a specific prediction tied to any one mountain. Etna's slow flank movement is one piece of a much larger regional puzzle, not the headline act of that particular statistic. There's good historical precedent for taking the broader risk seriously, mind you. One of the most destructive tsunamis recorded in antiquity happened back in 365 CE, triggered by a major earthquake off the coast of Crete, powerful enough to actually lift parts of the western end of the island by several meters. That event sent waves crashing into coastlines right across the eastern Mediterranean. So this isn't some entirely theoretical modern worry dreamt up to justify a research grant. The region has form. What I find genuinely reassuring about this section of the story, though, is how it's actually being treated by the people responsible for preparedness. There are large-scale international tsunami exercises run periodically across the region, coordinating scientific institutions, national governments, and civil protection agencies, essentially rehearsing how warnings would get communicated and how evacuations would actually work if a real event occurred. There's also an ongoing program working to get individual coastal communities formally recognized as properly prepared, with things like clear evacuation routes and practiced response plans, gradually expanding that recognition to more and more towns across the region year by year. That's the tone I want you to leave this section with, honestly. Not, the Mediterranean is a ticking time bomb nobody's paying attention to, because that's simply not true. It's, this is a known, well-studied regional hazard, with serious institutional effort going into understanding and preparing for it, in much the same patient, unglamorous way the people watching Etna's flank are doing their work. Slow science, slow preparation, running quietly in the background of a region most people only ever think about for its beaches and its food. To give you a sense of what that international preparedness work actually looks like in practice, there's a major coordinated exercise called Wave 26 that's been running across the region this year, bringing together scientific institutions, national governments, and civil protection agencies from countries all around the Mediterranean, North, Baltic, and connected seas. It works through a series of rehearsed scenarios based on real historical events, one modelled on a 13th century earthquake near Cyprus, another reconstructing conditions similar to an 1867 earthquake in the Ionian Sea, involving both Italian and Greek monitoring agencies working together, and another still based on an 1887 earthquake that affected both France and Italy along the Ligurian coast. The point of running through old, real events rather than invented worst-case scenarios is that it keeps the exercises grounded in things that have demonstrably happened before, rather than in pure speculation. And the reason that kind of rehearsal actually matters comes down to timing, more than anything else. In some of the more vulnerable stretches of Mediterranean coastline, modelling suggests an earthquake close to shore could produce a tsunami reaching the beach in well under half an hour, in some scenarios closer to 20 minutes. That's an extraordinarily tight window for any warning system to work with, nothing like the hours of notice you sometimes get with a transoceanic Pacific event, which is exactly why so much of this preparedness effort focuses on rehearsing the human and institutional side of things, sirens, evacuation routes, community-level drills, rather than just the scientific monitoring alone. You can have the best seismometers in the world, but if a town doesn't already know instinctively which direction to walk when the alarm goes off, that scientific head start doesn't count for very much. I think that's actually the most important takeaway buried in this whole section, more than any individual statistic. The Mediterranean tsunami risk isn't being treated as some distant theoretical worry filed away for future generations to deal with. There are real exercises, with real countries, real coordination, happening on a genuine annual or near-annual basis, precisely because the people responsible for public safety in this region take the underlying science seriously, even while the rest of us are mostly just thinking about where to book our next beach holiday. The tsunami-ready recognition I mentioned a moment ago isn't just a badge handed out for good intentions either. Communities have to actually demonstrate things like clearly marked evacuation routes, functioning public alert systems, and a track record of running real evacuation drills with actual residents taking part, assessed against a set of defined indicators before they're formally recognised. A handful of towns across the wider region, including some in Italy itself, have already achieved that status, with the stated ambition of expanding the programme to many more coastal communities over the coming years. It's slow, unglamorous, committee-driven work, the sort of thing that never makes for an exciting news segment, but it's precisely the sort of work that actually determines what happens in the real, chaotic minutes after a warning siren goes off. Alright, I think we've now got more or less the full picture in front of us, mythology and geology and history and modern monitoring all laid out. Worth actually sitting with the question properly now, the one this whole video is built around. Right, let's actually answer the question properly, because I think after everything we've covered tonight, we're in a decent position to do that honestly, rather than just leaving it hanging the way a more sensationalist version of this video might. Part 1 of the answer is yes, unambiguously. The eastern flank of Mount Etna is measurably, consistently moving toward the sea, and has been for at least as long as instruments have existed to measure it. This isn't a contested claim or a fringe interpretation of shaky data. It's been confirmed by decades of land-based GPS readings, and then independently confirmed again by an entirely separate method, underwater acoustic monitoring, which is about as solid as agreement between two different scientific techniques tends to get. The mountain is sliding. That part of the title isn't an exaggeration. Part 2 is where it gets genuinely more interesting, and where I think a lot of the more breathless coverage of this topic tends to quietly lose the thread. Whether, or when, that slow creep might ever turn into a sudden catastrophic failure, the kind that would actually generate a major tsunami, is simply not something anyone can currently say with any precision. The researchers who did the original underwater monitoring work were careful to say they couldn't rule that scenario out entirely. They were equally careful, in the same breath, to say the immediate risk is low, and that if it ever did happen, we could plausibly be talking about a time frame stretching out 100,000 years or more. Possibly far longer. Nobody serious is putting a tighter number on it than that, and I think that vagueness is itself an honest, scientifically responsible answer, rather than a dodge. So here's how I've come to think about it, for what it's worth. This isn't really a ticking clock story, even though that's obviously the more clickable way to frame a video title, and I'll fully own that I leaned into that a little myself for the thumbnail. It's closer to being an extraordinary stroke of scientific luck. We happen to be alive at exactly the point in history where the instruments exist to actually detect and measure a process like this. A process that's probably been quietly happening for tens of thousands of years, completely unnoticed, long before anyone had the means to catch it in the act. Acoustic transponders pinging away on the seafloor every 90 minutes, patiently building up a picture of something that would otherwise be entirely invisible to us. That's genuinely remarkable when you sit with it properly, regardless of what the long-term outcome eventually turns out to be. And honestly, I think that reframing matters. Etna isn't a doomsday countdown. It's an active, ongoing scientific story, one where researchers keep adding new instruments, new data, new little pieces to the puzzle, with absolutely no expectation of some imminent dramatic conclusion. The mountain will probably keep doing more or less what it's been doing for a very long time yet. Erupting fairly regularly in the way we talked about earlier, creeping seaward by a few centimetres a year, mostly unnoticed by anyone except the people whose actual job is to notice it. I think it's worth saying something general here too, separate from Etna specifically, about what scientific uncertainty of this particular kind actually means, because I don't think it gets explained well very often. When researchers say something can't be ruled out, that's not scientific hedging or nervousness about committing to an answer. It's an honest, precise description of the actual state of knowledge. There simply isn't enough data yet on a process this slow to calculate odds with any real confidence, the same way you couldn't meaningfully predict the exact day a glacier might eventually carve a particular iceberg, even while being entirely confident that glaciers do eventually carve icebergs. The not knowing isn't a failure of the research. It's an accurate reflection of working at the genuine edge of what's currently measurable, on a timescale that dwarfs any single human research career, let alone a single funded study. That's actually one of the things I've come to like most about following this kind of slow-burn natural history story over the years, if I'm honest. There's no tidy, satisfying resolution waiting at the end of it, no big reveal where everything gets wrapped up and explained completely. The story just keeps continuing quietly, with researchers adding new measurements every year, new instruments, new small refinements to a picture that may never be fully complete in any of our lifetimes. I find that strangely restful to think about rather than frustrating. Some questions are allowed to stay open, some mountains are allowed to just keep doing their slow, patient thing indefinitely, fully documented and fully understood in terms of mechanism while remaining genuinely unresolved in terms of timeline. There's nothing wrong with that. It's just what honest, ongoing science actually looks like from the inside. There's actually something a bit fitting structurally about how long this video itself has ended up being now that I think about it. We've spent a good while working through mythology, then geology, then history, then modern instruments, then a fairly significant detour into other volcanoes entirely, before finally circling back to the actual question in the title. That's not me padding things out for the sake of it, I promise. It's genuinely closer to how the real research unfolded too, layer upon layer, each new piece only really making proper sense once the last one was in place. If the structure of tonight's video has felt almost geological in its own pacing, slow accumulation rather than one dramatic reveal, I'd take that as rather a compliment, honestly. I find that a genuinely comforting way to land on this topic, if I'm honest. Not because nothing's happening, plenty is, but because what's happening is slow enough and well enough understood that there's no good reason to lie awake over it. Which, given what this whole video is meant to be for, feels like rather a fitting place to be. Before I wrap up properly, I wanted to leave you with a handful of smaller bits and pieces about Etna that didn't really fit anywhere else, but that I quite liked finding along the way. That changeable height we touched on right at the start is worth coming back to briefly, because it's a nice little illustration of how alive this mountain actually is, structurally speaking. It's not just erupting on the surface, it's genuinely rebuilding itself constantly. Crater rims collapsing here, new material piling up there, so the summit you'd photographed this year might measure differently to the one from 5 years ago. Most mountains are essentially static on a human timescale. Etna just isn't, and I think that restlessness is part of why it's become such a valuable place for the wider field of volcanology generally, almost a working laboratory rather than a fixed monument. There's also a slightly unexpected connection to space exploration, of all things. The barren, otherworldly landscape up around some of Etna's older craters has apparently been used at various points for training exercises related to lunar missions, Astronauts and engineers getting a feel for navigating genuinely alien-looking terrain without having to leave the planet to do it. I rather like that an ancient Sicilian volcano has, in its own small way, played a role in humanity's attempts to understand other worlds entirely. There's also a surprising amount of life clinging on across the different altitude bands, which I didn't expect going into this. Birch forest partway up, wild orchids in places, foxes and falcons higher up than you'd think reasonable for an active volcano. The whole mountain works almost like a stacked set of separate microclimates, each one supporting things the others can't, purely because of how altitude and volcanic soil interact differently at every level. I rather like that detail, actually, because it undercuts the image of a volcano as purely a dead, ashen wasteland. Most of Etna, most of the time, is doing exactly what mountains generally do, growing things, supporting wildlife, quietly getting on with it, with the eruptions as more of an occasional dramatic exception to an otherwise fairly green and busy rule. And there's an eruption from the early 20th century worth a brief mention too, separate from the famous 1669 event we covered earlier. In 1928, lava flows destroyed the town of Mascali almost entirely, advancing fast enough that the destruction happened within a matter of days, rather than the slower, weeks-long build-up of 1669. The flow came remarkably close to reaching the sea before eventually stopping. It's not as famous as 1669, possibly because the death toll was apparently low thanks to a fairly swift evacuation, but it's a good reminder that flank eruptions, the lower down, faster moving kind we talked about back in the structure section, aren't purely historical curiosities. They're a recurring category of event this mountain produces on a fairly regular basis, with real consequences for the town sitting closest to wherever the next vent happens to open. There's also a slightly mad bit of more recent history worth a quick mention, from 1983, when an eruption that ended up lasting around 4 months prompted Italian authorities to try something rather drastic, deliberately detonating explosives to redirect a lava flow away from populated areas. It's apparently regarded as one of the earlier serious modern attempts at actively engineering a lava flow's path using explosives specifically, rather than the older, more manual approach. Pappalardo and his crew tried back in 1669 with picks and brute persistence. Different century, broadly the same underlying instinct though, looking at an unstoppable river of molten rock bearing down on a town and deciding reasonably that doing absolutely nothing isn't an acceptable option, even if the available tools for actually doing something remain fairly blunt. Across its whole recorded history, by most counts, Etna's racked up somewhere over 200 individually documented eruptions, which, when you sit with the 2,700-year written record we talked about right back at the start, works out to a genuinely active mountain by any reasonable measure, not just an occasional headline grabber that happens to wake up once or twice a generation. It's closer to a constant background presence in Sicilian life than a rare event, which I think is actually the single most important thing to understand about this place if you take nothing else away from tonight. I think that's everything I wanted to get through tonight. There's a lot more buried in the research that I genuinely didn't have room for, smaller eruptions, individual volcanologists with properly fascinating careers, the wine-growing side of things in a lot more depth, so if there's appetite for it, I might come back and do a separate one purely on life and culture on the mountain slopes at some point down the line. No promises on timing though, these things take a while to put together properly. For now though, I think it's time to let this one rest. It's funny, looking back over everything we've gone through tonight, how the story sort of folds back on itself by the end. We started with the ancient Greeks deciding that the rumbling under this mountain had to be a furious giant, trapped underground, still struggling to get free after being buried there by a god. And here we are, several thousand years later, with scientists pinging acoustic signals off the seafloor every 90 minutes, very patiently measuring more or less the same basic idea. Something enormous, slowly, quietly, on the move beneath the surface, mostly invisible unless you know exactly where and how to look for it. Same mountain, same restlessness, just a different vocabulary for describing it now, centimeters a year instead of an angry buried titan. I don't know about you, but I find there's something rather lovely in that. The myths weren't wrong to sense that something was moving down there, they just didn't have the instruments yet to say so properly. Now we do, and the actual answer turned out to be its own kind of remarkable. No monster required, just a very heavy mountain, some ancient soft clay, and a great deal of patient, unglamorous science being done quietly by people who genuinely love this stuff. I think what I'll actually take away from putting this one together, more than any individual fact, is just how much patience the whole story requires. From the ancient poets who kept writing the eruptions down, generation after generation, to the researchers today happy to leave instruments running on the seafloor for over a year just to catch a few centimetres of movement. Nobody involved in any of this, across nearly 3,000 years of paying attention to this particular mountain, has ever been in a rush to fully understand it. Maybe that's the actual lesson worth sitting with as you drift off, more than any specific number or study. Some things are simply too large and too slow to be understood quickly, and that's all right. Anyway, that's where I'll leave it for tonight. Sleep well if that's what you're here for, and if you're still awake at this point, well, fair play to you. You made it through a fairly long one. I'll catch you in the next video.